Hi, today by using two examples, I'll show you how to prove that the limit of a function is the answer that it gives. We'll need the precise definition of a limit for this. In the first example, we have a linear function. And working with a linear function is quite simple. We don't require an additional step. I'll begin with writing the general precise definition of a limit. It states that for all epsilon that's positive, there exists a delta that's positive such that function f of x minus the limit is less than epsilon for all x such that 0 is less than x minus a less than delta. Here, such that and those two dots mean the same thing. They are just written differently. And now I want to show that A here shows what x is tending to. L shows the limit and f of x is the function that is given. Now let's write a definition that's exactly for our case. For arbitrary epsilon that's positive, there exists a delta that's also positive such that our function, which is 3x plus 2 minus the limit 14 in absolute value is less than epsilon for all x such that 0 is strictly less than the absolute value of x minus a, which is 4 in our case, is strictly less than delta. Now don't forget to write let epsilon be greater than 0, because otherwise whatever you are writing in your proof doesn't hold. First step of this proof is to guess the delta, but we don't really guess in here. We'll come to an answer mathematically. So what we should do is that now that we have 3x plus 2 minus 14, somehow we have to have x minus 4 on one side of the equation. By writing the equivalent signs, we will just come to an answer by working on this equation. Now, as you see, we factor out 3 and we have x minus 4 as we needed to. The next step is to just divide both sides of the equation by 3 and we have epsilon over 3. We can set the candidate delta equal to epsilon over 3 because it doesn't depend on x. And now we have to prove that this delta really holds. So that brings us to the second part of our proof. I also want to mention that this interval, epsilon over 3, is the largest interval possible. For the second step of our proof, we have to write that for all x such that 0 is strictly less than the absolute value of x minus 4 is strictly less than delta, which is equal to epsilon over 3, because this is our candidate delta. I'll mark this equation with a star because we'll motivate our step with this equation. This part that we wrote is the same as the second part of the definition that we have written for this case. That's why we have to come to an answer where we have just epsilon in the other side of the equation. Now again, by working on the equation that we have, 3x plus 2 minus 14, we again factorize it to a point where we have x minus 4 in our equation. Now this equation is just less than 3 times epsilon over 3. We motivate this step by the equation star that we have written down earlier. And by just factorizing, we have epsilon on this side of the equation. And of course, you can't forget to write the conclusion. We write hence, limit x approaching 4. You could write f of x here. I just wrote down the function 3x plus 2 is equal to 14. Indeed. Now let's look at a more complex example. Here we have a quadratic function. I will again begin by writing the definition. For all epsilon positive, there exists delta positive such that the absolute value. You could write f of x for general, but I'll write for our case x squared plus 3x plus 2 minus 0, which is the limit, is strictly less than epsilon for all x such that 0 strictly less than x minus 1 in absolute value less than delta. I'll just rewrite this part where x minus 1 is just x plus 1, so I'll just rewrite that. And of course we begin with writing let epsilon be greater than 0. Never forget this step. We'll work with the function that we have and come to a point where we have x plus 1 on one side of the equation. We write this down by the equivalence signs. Again, the notation is really important here. If you don't write some part of the notation, you face a problem. Now we'll just factor this quadratic equation, and we just have x plus 2 and x plus 1 as we needed on one side of the equation. However, by bringing x plus 2 to the other side of the equation, we can't choose this as a candidate delta, because look at that. This depends on x, and delta can't depend on x. To visualize it, I'll just draw an interval with 0 not included, of course. And for simplicity, I'll assume that delta is less than or equal to 1. You could choose any value here. It could be 2, it could be 10. The numbers will change in the proof, but again, you'll come to the same conclusion. You can try it for yourself. Now the interval is between -1 and 1. Because here we have 0 minus delta and 0 plus delta. This implies that our x is between -1 and 1. I will mark this step by a yellow star because later when we motivate our steps, it will be just easier to refer to some equation. Back to finding our candidate delta. At first, I wrote this because I wanted to let you guys think if there's something wrong with it. But of course there is. I'm gonna explain it to you now. We write epsilon over 3 because of what we calculated earlier. Now back to the problem. Imagine epsilon is large. Imagine it's 30. Then our delta becomes 10, which is impossible. It contradicts our assumption. So for this to hold, we'll set delta, the minimum function, 1 epsilon over 3. So we can now move to the second part of our proof. We again write for all x such that 0 is strictly less than absolute value x plus 1 less than delta, which is equal to minimum 1 epsilon over 3. And we write what this means. It means the delta is less than or equal to 1 and delta is less than or equal to epsilon over 3. Now again, we just write the function and factorize it. To be able to motivate my step, I will add a green star above this equation. And by star, it means that the left-hand side is less than absolute value of x plus 2 times epsilon over 3. And this is also less than, which is less than 3 times epsilon over 3. We motivate this step by the yellow star. And by just factorizing again, we got epsilon on the right hand side of the equation. And of course, we don't forget to write the conclusion. Limit x tending to -1 of x squared plus 3x plus 2 is indeed equal to 0. Thank you for watching.